Why? Lower inlet main steam pressure and temperature increases specific steam consumption in steam turbine. We'll learn with practical calculations in this video. Hello friends, welcome to my YouTube channel Power Plant Practical Knowledge. Previously, we learned reason for increase in turbine specific steam consumption with respect to lower vacuum. Today we will learn the reason for increasing turbine specific steam consumption with lower inlet main steam pressure and temperature. How much effect or specific steam increases with lower inlet main steam pressure and temperature? What are the effect it will have on the steam turbine? What is the cause and what are the precautions need to be taken by operator by monitoring and to avoid the increase in specific steam consumption? First, we will understand by calculation how much the specific steam varies with lower inlet main steam pressure and temperature when compared with high pressure inlet steam pressure and temperature. For calculation, we will consider the same 20 megawatt turbine operating with vacuum 0.9 kg per centimeter square. Here we will take two different cases. One at low pressure, at pressure 65 kg per centimeter square and temperature 490 degrees centigrade, and next at pressure 87 kg per centimeter square and temperature 515 degrees centigrade. In both the cases, vacuum remains same at 0.9 kg per centimeter square. We will calculate for both these conditions and let us know how much the specific steam increases comparing both the cases. We will use the same formula. P is equal to Q into enthalpy of inlet steam minus enthalpy of exhaust steam divided by 860, because 1 megawatt is equal to 860 kilocalorie per second. For calculating the flow, we will slightly modify as per our requirement. Now consider inlet pressure at 65 kg centimeter square and temperature 490 degrees centigrade. For this inlet steam conditions, enthalpy will be 810 kilocalorie per kg. Substituting the values, power P is equal to 20 megawatt into 860 divided by 810 minus 619. 619 the enthalpy of exhaust steam at vacuum 0.9 kg per centimeter square, and substituting all these values and calculating, we are getting the steam flow is equal to 90.05 metric tons. This is the steam flow required at 65 kg per centimeter square pressure and temperature 490 degrees centigrade. Now we will calculate the steam flow required at pressure 87 kg per centimeter square and temperature 515 degrees centigrade. At this inlet condition, enthalpy of steam is 818 kilocalorie per kg. Substituting the values for same 20 megawatt turbine and at exhaust vacuum 0.9 kg per centimeter square, we are getting the steam flow is equal to 86.43 metric tons at pressure 87 kg per centimeter square and temperature 515 degrees centigrade. Now you can clearly observe the decrease in steam flow. It's almost nearly 4 metric tons for same 20 megawatt load generation. Now you can clearly conclude that lower inlet main steam pressure and temperature increases specific steam consumption. Now it's clear that turbine operating at pressure 65 kg per centimeter square and temperature 490 degrees centigrade consumes more steam as compared to turbine operating at 87 kg per centimeter square and temperature 515 degrees centigrade. Now we'll understand what are the causes for lower main steam inlet pressure and temperature. One of the major issues among them is the boiler issues, incomplete combustion, poor fuel quality, or feed water heater problems. For example, if you take a Cogen boiler, nothing but boiler in the sugar plant, what happens? The fuel we get is from the mill. This fuel is nothing but the online fuel. After crushing, after extraction of juice, the bagasse will be sent to the Cogen. As it comes directly from the mill, there will be a moisture of around 48%. Sometimes what happens if there is any problem in the mill side, this due to improper crushing in the mills, pole and moisture escapes in the bagasse. When there is a wet bagasse enters the furnace temperature drops, and the air what we are supplied at that rated load will be the excess air which cools the furnace temperature drops. This will affect the main steam temperature and pressure. Similarly, in coal fired boilers, when wet coal enters the furnace, it lowers the furnace temperature, causing to reduce the pressure, simultaneously the temperature of the main steam, which will enter the steam turbine. But as the load is fixed, this lower pressure and temperature at same load increases the steam consumption. For same load, this will increase the specific steam consumption. Another reason is the header bar pipeline defects, malfunctioning de-superheater spray valves, or excessive pressure drop across main steam lines. At partial load, if we close the de-superheater valves also, there will be a slight passing of spray. What happens? This spray automatically reduces the pressure and temperature of the main steam. Again, this will lead to the specific steam increase in the turbine. Another reason is the pressure drop in the main steam line. This will also lead to the increase in pressure specific steam of the turbine. Next is operational swings, high unmonitored steam extraction demands from industrial process. Again, if we take the sugar plant as an example, we charge 3 atm steam to the process for sugar evaporator boiling. What happens if there is any load variation in the evaporator? The sugar side will extract the 3 atm steam more without intimation, or before we change the load, they extract the steam. This extraction of steam will increase the specific steam, as extraction is steam is more, but the load is fixed before and after extraction of more steam by the process. Another reason is the carryover, boiler carryover in the steam lines, causing rapid temperature drops, as the carryover causes the scaling formation on the superheater coils, affecting the heat transfer from the flue gas to the steam, reducing the steam temperature. This affects the total enthalpy of the steam, as the enthalpy is reduced for the same mechanical or electrical output. To produce the same power, the enthalpy need to be increased. To increase the enthalpy at reduced steam temperature, steam flow has to increase. This is the reason why specific steam increases at low temperature. Effect of lower inlet main steam pressure and temperature on the system. There will be lower enthalpy and output due to reduced heat energy, as it limits the work the steam can perform across the blades. And the reason is higher SSC, because available energy is lower, the mass flow rate of steam must increase to maintain the desired load. Another reason is the thermal shock. Sudden temperature drops causes uneven rotor to casing expansion. This will have the abnormal effect on the equipment, which also reduces the life of the equipment and increases the maintenance cost due to uneven expansion and thermal shocks on the turbine. Another reason is the blade erosion. Wet steam shifts into the early stages of the turbine, causing catastrophic moisture droplet erosion on the blades and corrosion. This erosion and corrosion will cause the uneven in the rotor, which leads to higher vibration. Turbine rotating at higher vibrations will reduce the life of the turbine. Another reason in the vibrations and failure. Due to all above reasons, lower pressure, lower temperature, condensed water slugs cause severe water hammer, severely damaging casing joints, labyrinth seals, and thrust bearings. Due to the low inlet pressure and temperature, abnormality arises in the system, which will lead to uneven casing expansion, increase in vibration. This will reduce the life of the equipment and the increases the maintenance cost. What are the precautions to be taken by operator to prevent lower mainstream inlet pressure and temperature entering the turbine and reducing the effect, its life, its maintenance cost? What are the precautions to be taken by the operator? By monitoring superheater margin, strictly ensures the main steam temperature stays well above the saturation temperature limit to prevent internal blade erosion. As the saturated steam, if it enters the turbine, it will cause the erosion of blades and the pittings on the turbine blades, which will reduce or hinder the turbine life. Another reason is control the ramp rates, increasing the load on the turbine or decreasing the load on the turbine. You need to follow the OEM guidelines for temperature and load changes to avoid thermal shock and casing rubbing, which, if not controlled or maintained, which increases the vibration, hampering the life of the turbine. Another precaution need to be taken by operator is to use drain valves. Keep main steam line drains and casing drains cracked open during turbine startup and low load operations to clear condensate and avoid water hammer in the turbines. Another precaution need to be taken by operator is to tune desuperators. Closely monitor attempted spray valves to prevent overspraying the main steam line, which will reduce the temperature of the main steam line. At partial loads, even if you close the desuperator completely, there is a chance of light passing of the desuperator, which will cause the main steam temperature to decrease and the water droplets entering the steam turbine. To avoid this, at partial loads, clearly monitor the desuperator valves. If the temperature is at decreasing trend, open the main steam line drains and crack open the casing drains and the main steam line drains to avoid temperature reduction. Another precaution need to be taken by operators or engineers is to keep healthy the interlocks and the production of the turbine. Verify that low pressure and low temperature interlocks and vibration trips are active and calibrated according to OEM manuals. Never bypass the turbine interlocks or protections, because if there is a low pressure or low temperature interlock is bypassed, and even if the engineer notices to observe the low pressure and low temperature and continuously starts to run the turbine, it will not only reduce the life of the equipment, or it may lead to major damage of the equipment and the persons operating in the unit. In many cases, this is observed where interlocks and protections are bypassed and severe damage to the life have been seen in many cases. So never bypass any turbine production or interlocks. So, from this explanation and the calculations, we are clear that lower inlet steam pressure and temperature reduces the turbine's thermal efficiency, causing a direct increase in specific steam consumption. The turbine requires more steam to produce the same electrical or mechanical output, placing higher thermal stress on the equipment and overloading of condensers. So, due to lower inlet steam pressure and temperature, there will be a reduced thermal efficiency, increase in specific steam consumption, leading to more steam required for same output. This will cause higher thermal stress and risk of overloading condensers for the same power generation. If you found this video useful, please like, share and subscribe. Your support and comments encourages me to make more such videos. Thank you.